So with rational functions, just remember rational, they're fractions. Okay. They're fractions. That's it. So your assignment over the weekend, that was all fraction operations. That's just to get you in the headspace of what do I do when I'm adding fractions, when I'm subtracting fractions, when I'm multiplying fractions, when I'm dividing fractions. That's the process. It's the same process. We're just adding in factor. Okay? But we're doing the same process. All right? So when we're looking at rational expressions, it's going to be an expression written as the quotient of two polynomials. That just means I have a fraction that's two polynomials. Numerator polynomial, the denominator is a polynomial. So we're going to start to see variables in the numerator and the denominator. All right? The big thing is that my denominator cannot be 0. What happens when the denominator of a fraction is 0? Not equal 0. And divide by 0. So if my denominator is 0, then it's undefined and it's not a polynomial or a rational expression anymore. But outside of that, hey, what do I write? Quadratic over a linear. I've got a binomial over a trinomial. I've got a monomial over a monomial. Okay? Those are all rational expressions. They're polynomials written as fractions. So again, a rational expression is undefined if the denominator is 0. And that plays into a really important thing that we're going to be spending some time on as well, specifically with domain, is that if we replace a variable with any number that causes the denominator to simplify to 0, then that value is a point where my function is undefined. It's fine everywhere else, but any value of x that would cause the denominator to be 0, we say that the expression is undefined for that value. Okay? It could be one number, it could be two numbers, it could be no numbers. We could be defined everywhere. It's fine. We just have to be on the lookout for any values of x that would cause the denominator to be 0, which most of the time isn't x equals 0. Very rarely is x equals 0 what causes our function to be undefined. It's other things, other numbers. And we're going to spend some time exploring this. Okay? So we want to find the domain of the rational expression. What does domain refer to? X values. All the possible x values of my function. So domain is possible x values. Okay? Or whatever our variable is, it's our input. The possible inputs. Now with a polynomial, any polynomial has a domain of all real numbers. Negative infinity to infinity. All polynomials have a domain of all real numbers. And we're going to transfer that assumption into the rational expressions with the exception of I need to exclude values that cause the denominator to be 0. Outside of that, it's everything else. So when we're looking at domain, the only thing I care about is the denominator. Look at the denominator. When I'm looking for domain, look at the denominator. And that's what the part is you're going to focus on, because that's going to tell us if I have any restrictions to my domain. Okay? So when I look at f of x and I look at 5, is there any value of x I could plug in that would make that 5 a 0? No. I mean, if I plug in 0, it just makes it 27 over 5, because that cancels and that cancels, and I have 27 over 5. That's not 0. There's no variable here. So there's nothing I could do that's going to change that 5 into a 0. So there's no restriction. So this one still has a domain of all real numbers. Negative infinity to infinity. Still has a domain of all real numbers. When we look at g, just looking at my denominator, are there any values of x that would cause x minus 2 to equal 0? 2. So when we're trying to find what values cause my function to be undefined, we take the denominator and we set it equal to 0. And we solve for x. If I add 2, I get x equals 2. That's the value that causes my function to be undefined. So my domain is going to be all real numbers except for 2. Okay? There's a couple different ways that we can write our domain. Okay? You'll see it a few different ways. All right? First way, set notation. Sometimes we just like to do set notation. So we have all values of x such that x is real. Okay? X is a real number. And x does not equal 2. So we're just saying, hey, it's all of our numbers except for 2. X cannot equal 2. So that's our set notation. The other way that we'll see it most often is the way that I write it is interval notation. Just like this. We're using this same notation here with our negative infinity to infinity. Okay? But what we have to do is we have to remember that we're skipping over 2. So I have negative infinity to infinity, but I have to have some stuff in the middle saying, hey, don't include 2. So negative infinity is going to go all the way up to 2. And then I'm going to skip over 2 and continue off to infinity. Anyone remember what we put in the middle when we're combining two intervals? A union. Put a union. And so we're saying that my domain is everything from negative infinity to 2. We're going to skip over 2 and then continue to infinity. All real numbers except for 2. Interval notation. And set notation. Interval notation and set notation. Those are the two main ways that you'll see domain expressed, especially with rational functions. Now for h, we're going to do the same thing. We're going to focus on the denominator and say, okay, x squared plus x minus 6 equals 0. So we need to figure out what values of x will cause it to be 0. So if I have a quadratic set equal to 0, how do I solve for x? Factor. It's going to be a lot of factors. A lot of factors. What are my factors? What two numbers? Not 6. Nope. There you go. Negative 2, positive 3. Multiply to give me negative 6, add to give me positive 1. Set factors equal to 0. Solve. Okay, so those are the two values that x is not allowed to be. They can't be 2, and they can't be negative 3. Everything else is fine. So we're going to use that same notation that we did down here, except I'm going to add in another union. So I'm going to have 3 sets of parentheses, because now I have an extra value that I have to skip over. I have to skip over negative 3, and I have to skip over 2. Okay? So it's going to be a little bit longer. All right, I'm going to write it up here at the top, because that's where I have the most room. Okay? So, our domain for h of x, okay? Domain for h of x. H of x, if I could write h of x. There we go. Okay? So, we're still starting at negative infinity. And then we're going to where? Where's the first place we're going to stop and skip over? Negative 3. Okay? And then negative 3 is going to continue till where? Till we hit to 2. And then 2 is going to continue until where? Infinity. So, negative infinity to negative 3. We're going to skip over negative 3, and then go from negative 3 to 2. We're going to skip over 2, and then continue off into infinity. If I wanted to do set notation, it would be very similar. It would be that x is real and x cannot equal 2 or negative 3. Okay, so the interval notation would be very similar. We're just changing that value that x cannot equal. And then our interval notation is going to have more unions as we add in more values to exclude. So that's domain. Yes?
We're going to need to know how to do both, or we just use the one way.
I will get back to you on that. I haven't decided. Actually, I need to look at what I did in my test last year and see. As for domain, okay, we're going to be doing multiple other things today. Okay, but for domain, the only thing I need to focus on is the denominator. Set it to 0, solve, find the excluded values. Yes, ma'am.
Quick question, so why did we include the 8 from the other question? So we just did like find out all 3. Like we combined.
What 8 are you talking
Okay, so I'm saying, so you wrote the domain of h of x at the top, and you did infinity to -3, -3.
So why do we have this right here?
Yeah, why do we?
So because I have 2 excluded values. X is not allowed to be -3 and x is not allowed to be 2. But I have to have a domain that includes everything else. So I have all the numbers before -3. I have all the numbers between my 2 excluded values. And I have all the numbers after 2. So if you look at a number line, I've got -3 and I've got 2, right? Those are the 2 values that aren't allowed to be in my domain. So I have to have an interval notation that gives me all of these other numbers. This one, the only excluded value was 2. So I only needed to include 2 sections. This one has 2 included values, so I have 3 sections that I have to include in the interval. For domain.
Okay.
For domain. Only for domain. We will use the numerator for other things, but not for domain. Okay? Domain, denominator. A little alliteration for you. Okay? Now, the rest of what we're going to be doing today is essentially simplifying or some form of it. Okay? It's going to be a lot of simplification. So the idea of simplifying fractions is that if we have a common factor, that common factor reduces to 1, essentially eliminating it from the fraction. So if I have, let's say I've got 15 and 27, okay? 15 has factors of 5 and 3. 27 has factors of 3 and 9, okay? They have this common factor of 3 that allows me to simplify my fraction and put it in lowest terms. We're doing the same thing with our rational functions, except instead of just splitting apart numbers, we're factoring the polynomial. So it's a more involved process, but it is the same exact principle. Factor the number, factor the expression, and then eliminate common factors, okay, in pairs. The big thing with simplifying is you need to make sure that it ends up in lowest possible terms. So for example, if I had 10 over 20, well, those have common factors of, 4, okay. Those have common factors of 5 if I split it apart as 2 and 5 and 2 and 4. So I can eliminate this and be left with 2 and 4, but that's not in lowest terms because I didn't eliminate all the common factors. I have another common factor of 2, which I would need to eliminate to get it in lowest possible terms. So that process applies with rational functions as well. We need to make sure that we are factoring completely GCFs, difference of squares, factoring trinomials. We need to factor as much as we can and get all those little pieces so that we make sure that we are eliminating as much as we can when we simplify. Okay? So, my numerator's already factored. So there's not really a whole lot I can do there. Okay? Denominator. I need to factor 12x to the third minus 3x squared. How can I factor that? GCF, what's my GCF? 3x squared. So I factor out 3x squared, and I'm left with what? Minus 1. Okay. Now we look, numerator, denominator. Do I have anything in common? 3x squared. They have that entire thing. So what's left in my numerator? 1. And in my denominator? 4x minus 1.
That's the answer.
That's it.
So the numerator is supposed to.
Yeah, so we're just looking for things that are in common with both sides. And then we can simplify those like we would a fraction when we have the common factor. And so I can divide both of these by 3x squared, which gives me a 1 in the numerator, and it leaves me with 4x minus 1 in the denominator. Okay? What about the one on the right? I need to factor my numerator.
Take x squared.
Okay, I'm glad you did that. It's a mistake, but it's one that happens all the time. I'm so glad you brought it up. Okay. Trust me, this happens. I've had calculus students do this. Okay, so don't feel bad
Oh,
about it.
because it's a negative.
Not because it's a negative. Is this only multiplication? Or do I have addition and subtraction? I have addition and subtraction. So these are not factors. X squared is not a factor, so I can't eliminate it. It's a term. So before I start to eliminate, I have to factor both polynomials. Okay? So let's factor x squared plus 3x minus 4. Come on, guys. That's a pretty simple one. Multiplies to negative 4, adds to 3.
Okay, so negative 4. Wait, no.
There you go. That's my numerator. Now, if we're simplifying, take it as a hint. You get your numerator factored, you're probably going to see one of those factors in the denominator. Okay? So now let's think about our denominator. X squared minus x minus 20. Factors for what? Plus 4 minus. I had to think about those signs for a second. My brain had to reboot. Now that it's factored, what do they have in common?
Plus 4.
So now that's a factor, in parentheses. That's a factor that they have in common, so I can eliminate, leaving me with x minus 1, x minus 5. And then again, I can't simplify this anymore because these aren't factors, these are terms. So they don't have any factors in common. They have common terms, but that's not going to help us simplify. Okay? It's going to be basically this. Okay? For a lot of what we're doing. Probably 70% of our work is going to be factoring and simplifying. Alright? So I've got 8 plus x and I've got x plus 8. Those are close, but they're not the same. What can I do? Well, I mean, alright, it's kind of already factored. I've got linear, there's no common factor. Okay, what do you want to do then?
Plus can swap.
Right. Our commutative property of addition says that the order of addition doesn't matter. So we could switch that into be x plus 8 over x plus 8. And now, these are exactly the same. Equals 1. Sort of. They're close, but that's subtraction, right? And they're switched.
Subtraction.
So now there's negative.
So, these are really close, right? But this is a positive 7, and this is a negative 7, and this is a negative y, and this is a positive y. What can I factor out that leaves all the values the same, but swaps the sign?
Negative 1.
Negative 1. So if I factor negative 1 out of either of those, doesn't matter, I'm just going to do the numerator. Negative 1. I factor out a negative 1, that's going to change that into a negative 7. That's going to change that into a positive y. Hey, now I have my commutative property of addition. So I can rewrite it as negative 7y minus, negative 1 y minus 7 over y minus 7. Now I have those common factors to eliminate, leaving me with -1. So if they're the same term, it simplifies to 1. If they are, same factor. If they are opposite factors, we factor out a -1, then we can simplify. So opposite factors simplify to -1. Opposite factors simplify to -1. Okay? 48 minus 3x squared. I need to factor it. Before it's a difference of squares, what do? Factor out the 3. So then I have 16 minus x squared, which then factors as a difference of squares. 4 minus x, 4 plus x. Okay, there's my numerator completely factored. Now let's look at the denominator. How do I factor my denominator? Okay. All right. What do I have in common? They're close. I have to factor out the -1 so that the sign switches. These are opposite factors. Okay? So they're opposite factors. So if I factor out a -1, then I get x minus 4. And then 4 plus x stays the same. X minus 4, x plus 1. Now those will eliminate. What's 3 times -1? -3. So I end up with -3, 4 plus x. Come on. Stupid eraser. 4 plus x over x plus 1. Okay? X cubed plus 8. Yeah, it's a sum of cubes. I've got a sum of cubes, so I've got x plus 2, x squared minus 2x plus 4. That's my sum of cubes formula, and then I've got 2 plus x. Do I have anything in common? X plus 2 and 2 plus x, because this is essentially x plus 2 using commutative property. So then those eliminate, leaving me with just the quadratic. I have nothing left in my denominator, so it's over 1. You don't need to write over 1. It's not going to make a difference. Remember, with sum and difference of cubes, that quadratic is usually not factorable anymore, unless there happens to be a GCF that you missed earlier. Later, when we spend more time with quadratic formula, we'll talk about ways to identify whether or not something is factorable without having to spend the time to figure out real quick to see whether or not you can factor it. Okay? Now, any other questions on simplifying? All right. Multiplying is simplifying. That's what it is. Multiplying is simplifying. All right? We're using that same idea of when I multiply fractions, I just multiply straight across. So my two numerators become factors of the same fraction. My denominator becomes factors of the same fraction. Usually with when we're multiplying, we're not actually going to multiply everything together until the end. Because when we're simplifying, we want to factor everything. So leave it factored and then maybe factor it a little bit more and just look for commonality between the two. So when I look at my first fraction, I can just go ahead and write it as 6x squared times 5x over 10x cubed times 12. It's all one big fraction. And now I can look for things that are in common. I'm going to group my numerical coefficients together just to make it a little bit easier to see. All I did was rearrange it so that all my numbers are in the front, my variables are in the back. So let's take it one step at a time. 6 over 12. Does that simplify at all?
Yeah.
1/2. Oopsies. Let's forget to take it back to a head. Alright. So I get 1/2. Okay? Highlighter. Alright. Then look at the next part. 5 over 10. Does that simplify? 1/2 again. So that comes down to 1/2. Okay? All multiplied together. And now let's look at the next part. I've got x squared times x over x to the third. It cancels completely, right? Because x squared and x to the third will cancel to just be x in the denominator. And then I've got x over x. That eliminates all together. So now I'm just doing 1/2 times 1/2, which is 1 times 1 over 2 times 2, which is just 1/4. Yeah, if you want to go ahead and multiply and kind of rearrange things for simplification, that's fine. You know, if you've got 30 over 120, and you see, oh, okay, if I multiply together 30 over 120, yeah, that'll simplify. That's fine. Yeah. The idea is just looking for common factors, whether you need to break them apart more or combine them a little bit. I could have taken this, if I wanted to, could have definitely done this, and had x to the third over x to the third and simplify from there. That's fine. Or you could break it apart more as x times x times x over x times x times x. So it's whatever you have to do to manipulate that and either break it apart or compress it so that you can see where the common factors are and you can simplify accordingly. When I've got binomials, or I've got polynomials, I want to kind of split everything apart. So again, I can start out looking at this as just one big fraction. All right? Now I've got m minus n squared. So I'm just going to go ahead and write it twice. Okay? Just to make it a little bit neater. Do I have to? No. Can I simplify without doing that? Yes. But you just have to be careful about making sure that you're eliminating the right things. Okay? So my denominator is m plus n. That's already factored. Can't do anything else. What about m squared minus mn?
It's the same thing.
So what do I have to do to factor it? Factor out the m. Factor out the common factor. Factor out m. Then I'm left with m minus n. And so now I have this completely factored and I can look for what's in common. Okay? So I'm just going to go down the line. M minus n. Do I have one of these in my denominator? Yep. Okay. M minus n. Do I have another one in my denominator? Nope. So I skip it. M. Do I have one of those in my denominator? Yeah, I don't have another m minus n. So I have to have one for each one that I wanted to eliminate. So I'm left with m minus n over m plus n. And again, those aren't factors, so I can't simplify anymore. Those are terms. Okay, so that's multiplying. Next, we're doing division. Division is multiplying with extra steps. And multiplying is simplifying with extra steps. So division is simplifying with extra steps. How do I divide fractions? Multiply by the reciprocal. Keep, change, flip. Okay? Multiply by the reciprocal. So I'm going to take my first fraction and I'm going to go ahead and split the square just so it's written twice, but essentially I'm leaving it alone. Changing the division to multiplication and writing the reciprocal of the second fraction. And we'll save ourselves a little time. How can I factor 5x plus 15? GCF of 5. So go ahead and save ourselves a little time and go ahead and factor that now while we're doing the flip. 25 on the top, yep. So then, hey, one big fraction now that we're multiplying. So look for common factors. I've got x plus 3. Do I have one in my denominator? Yep. X, see, I just made one big fraction because it's all together, right? X plus 3. Do I have another one? No, so I leave it. Do I have anything to simplify with 25? 5 and another 5, right? If I multiply those together, I get 25. So bloop, bloop. So all I'm left with, so those became that, all I'm left with is x plus 3. So this and this eliminated, okay? I don't have another one of these. Then I looked at 25. Well, I've got a 5 and another 5. 5 times 5 gives me 25.
Oh.
Those eliminated.
So you just flipped it. And
Yep.
said, okay.
Keep, change, flip.
Got it.
There's a lot of rules.
Not really.
You don't. There's a lot of stuff you could do.
So
You're not gonna.
the big thing is factor, and then treat them like fractions like you've been doing since you were like 7. You've been using fractions for a long time. It's the same rules. Okay? Multiplying, dividing. Multiply it straight across, and then simplify. Division, keep, change, flip, multiply across, simplify. Simplify what we've been doing. When we get to adding and subtracting, that's going to be our next lesson in a couple days, is we have to make sure we have what when we're adding or subtracting fractions? Same denominator. And so that'll add in an extra layer. It'll be a little bit more complex with rational functions, but the idea is the same. The principle is the same. In order to add or subtract, we need a common denominator. If I'm multiplying, I just multiply straight across. If I'm dividing, I need the reciprocal of my second ratio first, and then multiply. Okay? Same rules as adding and subtract, or as operations with fractions, just we're adding in really the factoring part so that we can simplify. Okay?